In this final lecture about MIP solving techniques, we will talk about pre-solving and related methods. The agenda looks short. There will be a main pre-solving part, followed by a sidetrack on conflict analysis, and finally, we will say some words on restarts. Hereby, we cover the missing parts in our MIP Solver Flowchart. Pre-solving, which is applied in the very beginning, before we enter the main loop. Domain propagation, which is part of every node processing and can be understood as local pre-solving. And conflict analysis, which is an additional procedure to be applied after infeasible nodes. Let's start with the main topic, pre-solving.
The idea of LP presolving is to reduce the problem size, such that the linear algebra of the simplex algorithm can be speeded up during the solution process. Moreover, presolving tries to strengthen the LP relaxation. For LP presolving, it is typically important to have the ability to post-solve primal and dual solutions and the optimal basis. Here, post-solving means to map a solution in the presolved space back into the original space. For LP presolving, this implies that it needs to preserve duality. Of course, the more complicated presolving operations are, the more involved post-solving is. The requirement to not only preserve post-solvability of the primal, but also of the dual and the basis, might forbid for some presolving operations. Generally, we distinguish between primal reductions and dual reductions, for both LP and MIP presolving. Primal reductions are only based on feasibility reasons. We exclude, for example, certain values for variables, because we can prove there's no feasible solution where the variable takes this value, or we drop a constraint which can be shown to be redundant for every possible solution. Hence, by primal reductions, no feasible solution will ever be cut off. On the other side, dual reductions typically consider the objective function. A dual argument typically involves that the optimal solution does not deteriorate when fixing a variable. Hence, dual reductions may cut off feasible solutions, but they always ensure that at least one optimal solution remains. Note that this might even involve cutting off some of multiple optimal solutions. As a trivial example, consider fixing a variable that does not appear in any constraint. MIP presolving involves LP presolving routines, and even more. In particular, MIP presolving can again exploit integrality, for example consider rounding, disjunctive or lifting arguments. As a simple example, it can round fractional bounds of integer variables, as depicted here. Often, MIP presolving identifies problem structures, like the clique graph, the implied bound graph and so on. In MIP presolving, there is no need to preserve duality, simply because there's no concept of MIP duality. It only needs to guarantee the ability to post-solve primal solutions, and this allows to conduct some reductions in MIP presolving that are not possible in LP presolving. There are various easy presolve operations, which are important nevertheless. For example, presolving can remove empty rows and columns. Moreover, it can tighten fractional bounds of integer variables, or substitute fixed variables, if there is an equation which does consist of a single variable or of two variables, like the equation xj equal xk, maybe times some scalar plus some offset. Another presolving operation is bound shifting of general integers, which addresses general integer variables, which are constrained to two possible values. These can be shifted to the values 0 and 1. Consequently, the variable can be treated as binary during the search. This is convenient since there are procedures defined only for binary variables. Presolving can also replace singleton rows. Suppose there is a row which only has one single variable. Even though it is not an equation, so the variable is not fixed, it would just imply a new bound on the variable. Moreover, some constraints may also be normalized, for example in the case in which all coefficients are integral, so they can be divided by the greatest common divisor. Trivial presolving is really important in practice, because problem instances are often automatically generated and contain many artifacts that the solver is responsible to deal with. Another important motivation for presolving is that, often, A first modeling attempt is trivially infeasible. For example, there could be a variable fixed to a value that is not inside its bounds. By presolving, we want to recognize this quickly, before starting any solution process. A third point is that a software that cannot recognize such trivial things does not look trustworthy to users. The most important part of presolving is general linear presolving by minimal and maximal activities. Assume we are given a general linear constraint, A transposed x less than or equal to B. Further assume there is a lower bound vector L and an upper bound vector U. We define two quantities, the minimum activity and the maximum activity of the constraint. The first is defined to be the minimum of the left-hand side of the constraint within the feasible set, described by the bounds of the variables x. This quantity can be easily computed by just splitting the variables into those that have a positive coefficient and those that have a negative coefficient. For a minimal activity, the variables should contribute as few as possible. Hence, we apply the lower bound of the variables to all the aj's greater than 0. Vice versa, we apply the upper bounds to the negative coefficients of the constraint. Maximal activity is defined similarly, lower and upper bounds simply change roles. A trivial observation that can be deduced from the minimum activity of a constraint is that, if this quantity is larger than the right-hand side of the constraint, then the problem is infeasible. Moreover, if the maximum activity is less than or equal to the right-hand side, then the constraint is redundant. If the maximum activity is less than or equal to the right-hand side, then the constraint is fulfilled by every possible assignment of x, hence it has no effects to the feasible space of the problem. These two quantities can also be used to strengthen the bounds of each variable. Let us establish this reduction. Let xi be the variable for which we would like to strengthen the bound. We assume ai to be positive, the negative case is analogous. The first step for this proof by construction is to add a 0. We take the constraint, a transpose x less than or equal to b, and we add and subtract the quantity ai xi to the left-hand side. Now, we bring everything to the right-hand side. This gives an upper bound on xi in terms of the coefficients of the constraint, the right-hand side and the other variables. At this point, we estimate the two values A transposed x and AI xi from below, by using the minimum activity and the lower bound of xi, respectively. In this way, we have obtained a new upper bound on xi. Moreover, for integer variables, this bound can, of course, be rounded down. This whole procedure is called bound strengthening. To obtain a lower bound by bound strengthening, we use the maximum activity and apply a similar argument. A third observation consists in a process called coefficient tightening, which works for binary variables. Assume xi is a binary variable, let ai be greater than 0 and such that the maximum activity minus the coefficient of that binary variable is less than or equal to b. This means that, if we fixed xi to 0, then the remaining activity of the constraint would be less than b, so the constraint would become redundant. That's the prerequisite for coefficient tightening. In this case, we can pull out ai xi and reformulate the inequality as it is shown on the slide. Let's check that this actually holds. We need to consider two cases, xi equals 0 and xi equals 1. When xi equals 0, the first part of the left-hand side drops out, and the remaining part is just the maximum activity of the constraint under the assumption that xi equals 0. Hence, just by definition of maximum activity, the inequality holds. Observe that this is strengthening the formulation, because the new right-hand side is less than the original right-hand side. It remains to check the inequality holds for xi equals 1. In this case, the first term of the left-hand side is just the alpha max minus b. Hence we can cancel the maximum activity and move b to the right-hand side, and ai to the left. This would give the original inequality, hence proving that this formulation holds also when xi equals 1. Let's look now at a practical example of bound strengthening and coefficient tightening. We are given the linear inequality, 7x1 plus 8x2 less than or equal to 21, with x1 bounded between 0 and 3 and x2 between 1 and 3. Hence, the minimum activity is 8, which comes from the lower bound of x2. First of all, we apply the bound strengthening procedure, and we obtain 1 and 2 as new upper bounds for x1 and x2, respectively. At this point, we observe that x2 can only assume the values 2 and 3, so we can replace it by a binary variable y2, hence substitute x2 in the constraint by 1 plus y2. Since x1 became already binary after bound strengthening, now both variables are binary and the constraint has a maximum activity of 15. This allows us to apply coefficient tightening. By using the formula that we saw before for the variable x1, we reduce the linear inequality to a tighter one, which still has the same set of integer solutions. Applying the same to y2, we obtain 2 times x1 plus 2 times y2 less than or equal to 2. This we can scale by a factor of 2 and get x1 plus y2 less than or equal to 1. This is a clique. Would you have seen this from the original constraint? Let us do a little exercise. Get pen and paper and try to find upper bounds for the variables in the given inequality. Keep in mind that they are integer. Proceed in 2 steps. First, compute the minimum activity of the constraint. Then, use the bound strengthening formula for each variable individually. The corresponding slide is linked in the description. We will reveal the solution in 2 steps, making a 5 seconds pause before each step. Since all variables have positive coefficients, they all contribute with their lower bounds to the minimum activity. We sum up the products of coefficients and bounds and get -2 as a minimum activity. The first step is the same for each variable. 12 minus -2 equals 14 is the difference between the right-hand side and the minimum activity. Then, for each variable individually we add the contribution of itself to get the difference between the right-hand side and residual activity, that is the minimum activity without that variable. Now we can simply compute how much the respective variable can contribute by dividing this residual activity by the variable's coefficient. Since the variables have to be integer and we are computing an upper bound, we can round down that quantity. The results are that x1 cannot be greater than 5, and x2 and x3 can both not be greater than 1. You can double-check that by plugging in an upper bound of one variable and the lower bound of 2 others into the constraint. Let's now move to dual reductions. As already mentioned, these reductions ensure to keep at least one optimal solution, although they might cut off some feasible or even optimal solutions. A very simple dual reduction might consist in fixing variables that appear in no constraint, which might cut off some possible solution values. Then there's dual fixing, which consists in fixing a variable x to its lower bound if it appears in no equation, only with non-negative coefficients in less or equal constraints, or only with non-positive coefficients in greater or equal constraints, and has a non-negative objective value. This sounds like a lot to ask for, but it's actually quite intuitive. If in all less equal constraints, a variable appears only with positive or zero coefficients, then it can be fixed to a lower bound, since it is the best thing we can do, with respect to the feasibility of these constraints. A similar logic applies to greater equal constraints. By fixing a variable to its lower bound, if it has only negative or zero coefficients in these constraints, we make them as feasible as possible. At the same time, we are also providing some benefit the objective function, since in a minimization problem, fixing something with a positive objective coefficients to its lower bound guarantees the best possible objective value. Additionally, we need the variable to appear in no equation. Indeed, in this case, the argument that there's one direction in which the variable can always be pushed feasibly doesn't hold anymore. We can use the very same argument when a variable violates these conditions for exactly one constraint and aggregate the variables such that this constraint will be fulfilled. Briefly, probing is something like strong branching without LPs, only applying bound strengthening arguments. It is usually done only for binary variables. Precisely, we fix one binary variable first to 0 and subsequently to 1. For each of these two fixings, we apply the bound strengthening procedure for all affected constraints. Then, we analyze the consequences. In an extreme case, when both x equals 0 and x equals 1 are infeasible, then the whole problem is infeasible. If only one of the probing directions is infeasible, then the variable can be fixed to the opposite bound. If one of the probes implies a certain fixing for a variable, while the other probe implies a fixing to another value or even the same, then we can aggregate this information and present x2 in terms of x1. In this way, when x1 is 0, x2 will be a, and if x1 is 1, it will be b. Now assume that the two probing directions imply bounds on a common variable and not fixings. We can use the weaker one as a new bound for the common variable. Finally, single direction deductions can be stored in the implication graph. OBBT stands for optimization-based bound tightening. It is a relatively expensive presolving strategy which solves auxiliary LPs. In that sense, it is related to strong branching. But instead of changing the bounds of the variables, it changes the objective function. This makes it applicable not only for binaries, but also for general integers and continuous variables. The idea is to minimize and maximize each individual variable over the set of feasible solutions, thereby deriving tightest possible bounds. This procedure is typically not applied in MIP solvers, but is used in mixed integer nonlinear programming, where strong bounds play an even more important role than in MIP. Another type of reductions are multi-row and multi-column deductions. In particular, checking for parallel rows or columns. Assume the coefficient vectors of two rows or columns are parallel to each other, meaning they are a multiple of each other. Then, one of the two rows is redundant, hence can just be discarded. Two columns could be aggregated into one column, or we could introduce a dominance relationship between them. Parallelism can be detected efficiently by using a special kind of hashing and sorting algorithm. We might also check for dominated rows or columns where these vectors are not parallel to each other, but are dominating each other. An example is when there are two less equal rows, the first having the left-hand side equal to the second plus some additional variable, while the right hand is the same. In this case, the first row would dominate the second because it's stronger. Actually, the running time required to detect such situations is quadratic, which in many cases is not tractable. Therefore, the pairs to check for dominance are usually selected heuristically. There are further multi-row pre-solving operations, which we don't go into detail on. Another important observation is that sometimes continuous variable can be casted into discrete variables. This is, for example, the case when a continuous variable appears as the only continuous variable in an equation. The detection of disconnected components plays a role in many practical MIPs. If a MIP consists of two or more disjoint variable constraint sets, then they can each be solved separately. In fact, solving them within a common branch and bound would be very ineffective. When you branch on a variable from one component, you only reduce the search space for this component. For the other component, it gets effectively doubled, since you still have the full original problem on this other component, but now in two subproblems. Analytic center presolving is based on the neat observation that a variable that is equal to one of its bounds in the analytic center can never take a different value than this bound. Hence, it can be fixed. This again requires an auxiliary LP solve with the barrier algorithm, but without crossover. Finally, I would like to mention reduced cost fixing. Reduced cost fixing is not really a pre-solving operation, since it is not applied in presolving, but after an LP solve. However, it is used to derive variable fixings and bound changes. In that sense, it can be seen as a form of domain propagation or as a very simple cutting plane. As the name gives away, it requires the reduced cost vector, hence the dual solution, provided by the simplex algorithm or by barrier. As we know, in the simplex solution, the reduced cost will be 0 for the basic variables, while for the non-basic ones it will be non-negative at lower bounds, and non-positive at the upper bounds. By definition, the reduced costs tell the unit amount by which the LP value would change if the solution was shifted towards the other bound, away from the bound that this non-basic variable currently sits at. If there is a dual bound on the MIP objective coming from the LP and a primal bound, for example, from a heuristic solution, we can use this to tighten the bounds of integer variables. In particular, a binary xi which is 0 in the current solution can be permanently fixed to 0 when the reduced costs are larger than the difference of the primal and dual bound of the problem. This is because, if the variable is currently at 0, and we wanted to bring it to 1, the value of the objective function would be at least the lower bound plus the reduced cost, hence larger than the upper bound. So, there can be no improving MIP solution which has this variable at 1. This is what the reduced costs tell us. This can be done whenever reduced costs are available. For example, reduced cost fixing is used to strengthen local bounds in subproblems by using the local LP solution. Of course, this applies not only to binary variables, but also to general integers and continuous variable, even though it might only lead to a bound reduction, and not necessarily to a fixing. Moreover, reduced cost fixing can be applied globally from the solution of the original LP, or LP solutions obtained from cutting plane separation. Note that we could even exploit dual degeneracy to explicitly compute different reduced cost vectors. This means alternative dual solutions for one and the same LP. For global reduced costs, we store the best reduced cost for each variable individually. At the root, we might not yet have a good primal bound available. However, even if we find such a bound later in the search, the stored reduced costs will still allow us to fix a variable globally during the tree search.
That was a lot of material. Let's see how much you remember. Quiz time. First question. Presolving. A. Must not cut off feasible solutions. Or B. May cut off feasible, but must not cut off optimal solutions. Or C. May cut off optimal solutions. Second question. The maximum activity of x1 minus x2 plus 2x3 less or equal than 5, with x1, x2, x3 all in 1, 2, is A, 2, B, 5, or C, 6. And third question, which of the following is not a goal of presolving? A, shrinks the problem size, B, find an initial solution, or C, strengthen the AP relaxation. That's the time to think about. Maybe pause the video. And here we go for the answers. First question. Presolving, indeed, may cut off optimal solutions. Dual presolving methods might do this. It must only ensure that at least one optimal solution is preserved. Second question. The maximum activity of this constraint is 5. And third question. Which of the following is not the goal of presolving? That's finding an initial solution. This is the task of primary heuristics. So, let us now continue with a technique that is different from presolving, but also useful to strengthen the problem formulation during the search. Conflict analysis is strongly connected to domain propagation, hence to local presolving. Firstly, domain propagation can trigger conflict analysis. Secondly, conflict analysis generates new constraints which are later used for domain propagation. Let's see what this all is about.
The motivation for conflict analysis is that half of the nodes in a binary branch and bound tree are pruned. Obviously, all the leaf nodes will be pruned, either because they exceed the primal bound, because we found a solution, or because they are infeasible. Exceeding the primal bound can be treated as a special case of infeasibility. What we want to achieve with conflict analysis is try to learn what led to the infeasibilities. The idea is to generate valid constraints that explain the reason of infeasibility, and to use those constraints to further prune the tree in the remainder of the search. There are two sources for such an infeasibility. One of them is local pre-solving, also called domain propagation. The other is the infeasibility of the LP relaxation. The idea for conflict analysis comes from SAT solving, where the variables are only Boolean, hence binary, and all constraints are clauses over literals. A literal is either a binary variable or its complement. A clause simply says that one of these literals must hold. Hence, in each clause, at least one of the non-complemented variables in the clause has to be true or one of the complemented variables has to be false. The task is to find an assignment for which all clauses are feasible, or to prove that no such assignment exists. SAT is the most fundamental NP-complete problem, since it was the first one for which NP-completeness was shown. Such a problem is, of course, trivial to reformulate as a binary MIP. In SAT solving, the working horse is unit propagation. If all but one of the literals are fixed, then the last literal can also be fixed. For example, assume we are given the clause that says either x6 equals 1, or x7 equals 0, or x9 equals 1, or x10 equals 1. Hence, if x6 is fixed to 0, x7 to 1 and x9 to 0, then, in order to fulfill the clause, the last literal x10 must be fixed to 1. The logic of unit propagation can be depicted in a directed graph, where each of the variable fixings corresponds to a vertex and implications or propagations are depicted by arcs. For example, the deduction of x10 equal to 1 that we saw on the previous slide could be part of such a graph. The fixing x10 equal 1 corresponds to a vertex. The propagation step corresponds to the set of ingoing arcs of that node. The variable fixings that led to the propagation are the source nodes of this arc set. We also call them an explanation of the bound change. With this tool at hand, we can conduct our global search and build up such a conflict graph. In this graph, each of these green nodes corresponds to one of the branching decisions, while the inner nodes represent propagations that have been made. For example, fixing x1 to 0 leads to x2 being fixed to 1 and, later, this fixing together with x4 fixed to 1, implies x5 being fixed to 0. The deduction that we have made before is part of this conflict graph. This process is then repeated until a conflict is detected, that is an infeasibility. This happens when one of the clauses tries to suggest a propagation that cannot be made. For example, here, x14 has been fixed to 1, x15 has been fixed to 1, and x13 has been fixed to 0 from all the propagations and branchings that we did before. However, there is a clause which says that, for at least one of the three, the opposite must hold. Hence, the search can be stopped here. So, this graph captures the ensemble of logic deductions that lead to the current state of infeasibility. What we can do at this point is to look at cuts in this graph. That is, cuts in a graph theory sense, a set of arcs that, when removed, separates the graph into two components. Every cut that separates the branching decisions from the conflict vertex gives rise to a valid constraint for the SAT problem. For the source nodes of the arc set which represents the cut, one of the opposite statements must hold. Let that sink in for a moment. In the cut depicted in the figure, at least one of the variables x6, x7, x8 and x12 has to take a different value. Hence the disjunction over the complements of their current fixings is a valid constraint. Why is that? Because, whenever in the remainder of the search, these four variables would be fixed to the same values again, we could take the same series of propagations and detect infeasibility again. Thus, obviously, this combination can be permanently ruled out. This is encapsulated in the conflict constraint. With this, we will ensure that whenever three of these four variables are fixed to the conflicting values, The fourth one will be fixed to the opposite value by unit propagation. This avoids going into the infeasibility again. Conflict analysis avoids making the same mistakes repeatedly. There are two trivial cuts that can be derived from every conflict graph. The first one is called the lambda cut, the red cut in the lower picture, directly at the artificial node. This gives a constraint that is already in the problem, hence it is not useful. The other one is what's called the no-good cut, the green one at the branching decisions. This is not useful either because this combination of branching decisions has already been explored at the current node. Thus, the helpful cuts that we look for are of the type of our first example, that have inner vertices on both sides of the cut. It has been shown that first unique implication points are a good strategy to derive conflict cuts from, because they usually give rise to short conflict constraints. A unique implication point is a vertex that lies on all paths from a decision vertex to the conflict vertex. There might be several unique implication points, in which case the one closest to the root is considered the first unique implication point. In our example, this is x11. To generate the corresponding cut, all decisions implied by x11 and all follow-up decisions are put on the conflict side. You see the cut in the picture. There are two vertices from which the arcs in the cut origin. Hence, we get a two-elementary conflict clause. x3 or not at x11. Similarly, one could derive an FUIP cut from the second to last decision vertex not x6. A strategy of generating one cut per decision is called all FUIP, and that is what MIP solvers typically use. There are two more peculiarities when we talk about applying conflict analysis in MIPS instead of SAT. There are several differences between SAT solving and MIP solving. First of all, in MIPS the variables are not only binary. For conflict analysis, this is mostly a technical difference. Instead of considering fixings, we can just follow the very same argument by using bound changes. Then, we would get something that we call bound disjunction constraint, which is not necessarily a linear constraint, but a constraint that's as easy to propagate as the clauses from binary conflicts. A much more important difference is that the infeasibility is often detected by the LP, which means that there's no single constraint that finally implies the infeasibility. At a first glance, an infeasible LP means that the model constraint plus all of the bound changes together led to infeasibility, which is not very useful for conflict analysis. To overcome this, we can try to find a small subset of the local bound changes that still proves infeasibility. To do this, we look at the proof of infeasibility of the LP. This is an unbounded direction in the dual. This follows from the strong duality theorem. The simplex algorithm terminates when it finds such a ray in the ratio test, hence we have this information readily at hand. Obviously, only the bound changes that have a non-zero value in the dual ray contribute to the proof of infeasibility. This is complementary slackness. Thus, it suffices to use this subset as an initial conflict reason. Furthermore, we can try to greedily sparsify these dual ray. This means try to set the values that correspond to dual bound changes to 0 one by one. If such a reduced ray still proves infeasibility, we use this instead of the original ray. The less bound changes in the initial reason, the better. Look at the picture. The graph still represents the logic of domain propagations that have been applied. However, we assume that the local infeasibility is found by an infeasible LP. We further assume that the proof of infeasibility can be reduced such that only 4 variables contribute with a local bound change to the infeasibility. These are x5, x11, x13 and x15. Hence, the corresponding 4 vertices get an arc to the lambda vertex. Now, the vertex x11 greater equal 4 is the first unique implication point, and the derived conflict constraint would read as x3 or x5 or x11 less equal 3. Since infeasibility can occur at many places, also conflict analysis can be run at many places. As we saw, the easiest form are conflicts that are found during domain propagation. We discussed how conflicts can be derived from infeasible node LPs. A very similar strategy can be applied for bound exceeding LPs. But node LPs are not the only LPs that are solved. Also, when a strong branching LP or an LP solved in a diving heuristic is infeasible or bound exceeding, conflict analysis can be run. Conflict constraints are easy to propagate, but these give rise to a very weak linear relaxation. Therefore, they are only propagated but not added to the LP. Also, solvers typically ensure that conflicts get deleted after a while. This is reasonable since they are typically most efficient in the vicinity of the node where they have been created and where a majority of the literals are already fixed to a non-satisfying value. Rapid learning is a strategy to create conflict constraints by an auxiliary problem. It is based on the observation that when searching a MIP solution space with a SAT-like algorithm, this means without solving LP relaxations, often hundreds or even thousands of nodes can be solved relatively quickly. Hence, after processing the root node of a MIP and before starting the global search, we can conduct such a rapid SAT search. All information that is derived that way will be valid for the MIP search. In particular, this includes conflicts. But also branching statistics might be useful to initialize VSIDs or inference scores, and maybe the SAT search even found a feasible solution. Restarts are another example of a strategy that MIP solvers took over from SAT solvers. Restarting a solver consists in stopping the search process after a certain time, and then starting everything again from scratch. It's a very common practice in SAT solving and is becoming more and more common in MIP solving. The main motivation in the MIP case is that after a restart, more presolving operations can be applied. This will hold when during the search some of the variables could be globally fixed. This could, for example, be due to strong branching or reduced cost fixing. There are different triggers for a restart. For restarts at the root node, MIP solvers typically monitor how many variables have been globally fixed during root node processing, and if this crosses a certain threshold, the solver will restart. There are recent publications which indicate that a single restart during the tree search can also be effective in many cases. The rationale here is slightly different. This restart is used to change the search strategies, for example the branching rule, working limits for cuts and heuristics and so on, after the restart. The restart is conducted when the first strategy does not seem promising to solve the problem quickly. This is the crucial point for these technology, to predict whether the search would terminate soon or will still take for a long time, and hence a restart will not cost much in comparison.
Okay, let's maybe not restart the lecture, but let's finish it with a little quiz. First question. A conflict constraint is a set of variable bounds from which A, at least one has to hold in any feasible solution, or B, at most one can hold in any feasible solution, or C, all but one have to hold in any feasible solution. Second question. Conflict analysis for infeasible LPs uses A, a primal solution, B, a dual way, or C, the reduced costs. And third question, where do MIP solvers not restart? A, during the initial LP solve, B, during the cut loop, or C, during the tree search? Think about the answers. And we go for the solutions. First question. A conflict constraint is a set of variable bounds from which at least one has to hold in any feasible solution. Second question, conflict analysis for infeasible LPs uses a dual way. And last question, where do MIP solvers not restart? That's during the initial LP solve. Okay, so thank you very much for your attention. I hope you enjoyed this little series on MIP solving techniques, and see you later for the Q&A. Bye-bye.